In finance and investing, there's something called the rule of 72, and it works in a very simple way, where we divide the number 72 by the rate of interest as an integer, for example, 8%, 72 divided by 8, and that will give you an approximation of the length of time it would take for an investment to double in value. You can see on the screen already, if we imagine the principal is 1,000, we invest 1,000 for 60 periods with a rate of interest of 2%, then we take 72 and divide it by, in this table, I'm doing it one by one, by 1%, and we're estimating that it would double in 72 periods. If it were 2%, the value would double to 2,000 in 36 periods, and so on, reading all the way down. It really is quite straightforward. However, is it true? This is my problem. So, is the rule of 72 in compound interest? I set up a table with interest according to the sequence function, 50 rows, this single column, beginning with 0.01, 1%, and increasing in steps of 1%. So 1, 2, all the way down to 50%. And then I put 72 in cell E4. So divide E$4 by A8 hash. Remember, I use the sequence function in column A, so we use the dynamic array hash. Multiply by 100 to get from 1%, 0.01, to 1. I drag that down, and then we find that it doubles by period 72. Can we see that? Over on my second table over here, I've created a table to show the compound interest for this situation, where we begin with 1,000, or any value you care to name, earn interest on an annual basis. So here, 2%, £1,000, $1,000, interest due $20. So by the end of the year, balance carried down is 1,020, bring it down, compound interest kicks in, so 20 becomes 20.4, and so it goes on. When do we get to 2,000 in this column? Let's try and find out. There it is. It's around about just over 34, a little bit less than 35. It says actual doubling is 35, nearly. And so there's a difference. We're expecting 36, we get 35, there's a bit of a difference. And in fact, that's true all the way down. If I change that to 3%, this table reinvents itself, and the doubling should be in 24 periods, actually in 23.45. Let's see that. It more than doubles after 24, so it is a bit more than 23, isn't it? It begins with 1973, and by the end it gets to 2032, 2033, so it's somewhere between there. And my formula here, which I haven't shown you up until now, is this one. I can use the number of periods function, NPER, this way, with the rate at A10. We're not making any further payments, it's just a one-off, the principal. And the principal, the present value, is minus, as it should be, $3, this one. And then the future value from 1,000 to 2,000. So 263, 526, doubling. So I've filled that up and I've filled that down, and that gives me the actual doubling point. One of the purposes of this exercise then is to see if there is a difference between the theoretical doubling by 72 and the actual doubling by calculation. And we find these differences. Minus 2.24, minus 1, plus all the way down to row 50, where the difference is still 0.27. The question now is, what if it isn't 72? What is it? Well, let's find out. I did it this way. So I've got my 72, my constant 72 there, which feeds into here, which gives me the doubling point according to the rule. Then notice I've got difference squared to get rid of the negative signs. And then I sum all those differences. We notice that the difference squared. Then I add together all of the differences squared, and it gives me 9.05806, which is the sum of E8 to E57, right down the bottom. The sum of all the square difference. So it's actually known as SSE, sum of squared errors. And what I'm doing here, I'm going to show you Solver now. Solver can find how to minimize the optimum value of this minimized to give us the more accurate rule of thumb, which might be 72, and it might not, might be more than 72, might be less than. So let's find out. All we do is this, data, solver. I've done it already earlier, so here we are. We choose this cell, E5. We'd like to minimize that by selecting E4. So what's the actual value of doubling point if it isn't 72? And then make sure that it can't be negative. And we're using the GRG nonlinear routine. So we click solve fairly quickly. It's a trivial exercise for Solver. It says it's found the answer. Click OK. And there we are. We think that the more accurate value of the doubling constant is 70.2583, blah, 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 blah. And what you should be able to see is SSE is a little bit less than half of what it was, and the differences are smaller, makes sense, all the way down to really almost nothing. And so now we've optimized our situation, so we know that whilst the rule of 72 is not bad, the rule of 70.25832358 in this example is a little bit better. Put these on a graph on the right-hand side, you can see. That's the doubling by 72. That's the curve you get by interest rate and by value. And then down here, I've put the actual doubling rate, the red one, and the differences, the blue one. It's quite a nice graph, isn't it? It's a bit like an ogive. But anyway, so that's it then. If you put these two, the blue one here and the orange one here on the same graph, they virtually lie over one on top of the other. You can't really distinguish between them. Unless you draw the graph very big, you might see them there. So I put them on separate graphs, and I put the differences that I have in the appropriate column on the right-hand axis, and it gives us this information, this additional information. Well, there we are. That's checking the rule of 72 in compound interest with me, Duncan Williamson. Thank you for watching.